Okay, so here we go. The good news is we might get out of here early today. So that is kind of the plan actually. So I had to leave early for my morning lecture, but today probably just going to leave early, even though But I like to synchronize the two things. Anyway, okay. So where we left off on Monday was talking about Amazon's transaction processing, how the fact that they're a very big operation creates problems that have to be solved in some way, right? They have a lot of transactions per second, especially during busy times. And because many of those transactions involve external systems, they can't necessarily follow along with straight ACID properties all the time because that would slow down their system too much. Okay. So where we'll start is with the definition of what we mean when we talk about transactions. So if you're an ordinary person with no particular technical context, and I tell you a transaction happened, you're probably going to think, well, somebody bought something, right? You go to the store, you buy you buy a can of blue raspberry, and then you pay for it. That's the transaction, right? Or maybe some of you would think, oh, I go online, I pay off my credit card bill every month. That's a transaction. Sure, those are ordinary kinds of transactions. But for databases, we mean something a little bit different. So when we're talking about transactions in a database context, we mean an action that is a single logical unit, right? Trying to do one thing, but doing that one thing for the databases might involve multiple systems or multiple copies of the data. So, for example, if you create a new customer account in some system, that's probably going to create echoes to other systems. For example, if there is a business that does customer relationship management, right? One of the things they're going to do, you create a new account there, they're automatically going to create an entry for you in their customer relationship management system so they can follow up with you about stuff. Or you go to YouTube, right? You create a YouTube account and then, hey, they're going to have an entry in some database where they track all the things that you watch and whether you respond to any particular kinds of ads or not. So there are going to be, multiple things going on to what seems like you just be one thing. Anytime you update database contents, right? Most databases, there's a backup copy, maybe more than one backup copy. So if you upload a photo to Facebook, right, the logical unit there is Facebook gets the photo, they store it in one database, and they create a couple other copies of it to store somewhere else, right? So again, single logical unit involving multiple actions. Even processing a query, right? There might be some things that has to see if the database tables are available or the requisite contents that you're looking at are not being used by other system users, right? There could be multiple things going on there. Okay. So that's what we mean by transactions, a single logical unit that could potentially involve multiple machines. All right. Now, in general, transactions follow what's called a request and agreement sequence, right? So you ask to do something, the system checks whether it's feasible, whether it's permitted, and if so, lets you do it. So typical example, you go to Amazon, you try to add a product to your cart, right? Well, first of all, Amazon's got to check and see, is it possible to add that thing to your cart? So number one, it might be that was the very last one, and at the exact microsecond where just before you press that click button, somebody else had bought it or added it to their cart, and it's no longer available. And Amazon will say, well, no, very sorry, but it's gone. So they still have to check that. Or Amazon puts a cap on how many different things you can have in your cart at a time. We'll talk about why they do that. But so Amazon might also have to check, how many things do you have in your cart, right? You'd like to add this thing, but before you can add it, you got to push something else out because the cart's only so big. Anyway, things like you try to do stuff and the system says yes or no. Eventually, you get to the end point of your purchase process. You go to Amazon's checkout and you enter in your credit card, you pick your shipping option, right? Anything else you need to do, whether you're using bonus points or not using bonus points, whatever. Okay, and then the transaction will go through if all that stuff is correct. But if you picked an invalid option, like a credit card number that's wrong, you typed in a wrong number, then it's going to cancel and they'll say, oh, please try again with a different number. All right. Now, very often transactions as purchases have these kind of request agreement cycles with outside systems. Of course, if you're going to Amazon Amazon not only needs to see that your credit card number is valid, right, has a valid format, the proper number of digits, and you've entered in the CVV code, all that, but also Amazon needs to call up the credit card people and say, hey, is this person able to purchase this much stuff, right? All right. Now, in a well-designed system, any changes to the data don't happen right away. What happens, in a sense, the system pencils in the changes, and only once the system determines that the transaction is actually feasible and permitted do those changes become permanent, right? That prevents the I can't do this with this constant low hum. It's somewhere over that side. Pass notes if you got to, but you know, I hear the all right. Thank you. Anyway, until all parties are committed to the transaction, right? Until everybody says, yeah, we can do this, then the changes aren't going to happen yet. And that makes it easier to undo changes if something goes wrong, right? Because in a busy system like Amazon's, it's a real pain to have to go and undo changes when those changes may have actually gotten buried behind other various things happening in the system afterward, trying to access the same data. Okay. And we'll talk more about that in a little bit. So the front end process of a transaction is all the stuff that ordinary customers see, right? That's, you go to Amazon, they got the website, they got all the pages with the products on them. That's the front end stuff, the stuff that the customer sees. So the basic process, probably log in, browse around for a while, add some items to your cart, check out, pick your delivery options, and pay. Now it's important to recognize all of those steps. There's some flexibility in there, right? But all those steps are basically sequential. And the reason is, before Amazon would like you to log into their system so that they can track who you are and what you're looking at, stuff like that. Obviously, you have to add things to your cart before you checked out. I mean, I know they have the option where you can kind of like insta-buy something, but let's assume they don't, okay? So you have to add something to your cart, even if you're using the insta-buy option, right? You first have to select something to buy, and then you can buy it. Once you have your cart with some items in it, you can begin the checkout, right? It doesn't make sense to check out if there's nothing in your cart. And finally, only once Amazon's figured out all the stuff that's in your cart can they really talk about delivery options, because some delivery options will be feasible for some products and some not for others. Okay. Anyway, so all these things are basically sequential, and there's very sensible reasons why. Now, the back end stuff is all the stuff that the customer doesn't see, all the stuff behind the scenes at Amazon that they want to track. So a lot of those systems are internal. For example, Amazon has all of its analytics stuff. They track who looks at what products, any correlations between looking at products and looking at other products, or buying products and buying, other products. And of course, external systems, right? Anything that Amazon has to send notifications. If somebody is selling a product through Amazon, Amazon has to notify them once you bought it so that they can know to send it to you, right? Or anything, credit card people, whatever. And then this is generally going to cause some kind of cascade of database activity. There's a bunch of different operations that happen. So I'll draw a picture. I didn't draw this picture for the morning, but I'll draw it for you guys. So I think we might have just a little more time. I was a little late in the morning. Okay, so this is you. You're this black rectangle here in the corner. And you go to Amazon. Let's do Amazon in orange. Okay, just to give you an idea of the stuff that's going on. Okay, so you go to Amazon, and what are you trying to do? You want to, I don't know, buy a book, because that's what people do on Amazon. So you want to buy a book for some reason. Okay, let's move that over a little bit. Okay, so you're buying a book. Now, a bunch of things have to happen with that, right? First of all, inventory checks. Amazon needs to see, hey, is this thing actually in inventory, right? We know the website says it did, but at some point we got to make sure that the guys in the warehouse actually have access to it. And that, it's all right. Is it there? And Tell the warehouse guys, right? WH for warehouse. Tell them, where to find it. They'll get a notification. Hey, somebody just bought this book. Put it in a thing. Amazon will also need to shipping, right? Either Amazon's internal or UPS, or in weird cases, or even USPS, right? Or FedEx could happen too. But a lot of stuff, around here, of course, Amazon ships it themselves. And then those guys are going to send back some notification about how long it's going to take, right? What else? Analytics. Right? Who bought what? Who looked at what? Who clicked what? Right? Things like that. Those are the details that Amazon's going to track in order to, design their website better, because that's always constantly under evaluation, right? There may also be some communication with credit card companies, right? That's possible. Now, if you buy it all on Amazon points, right, you might need to do something with that. And the credit card company, if you contact them, there's going to be some response back where they give, a thumbs up or a thumbs down to the transaction. So there's a whole bunch of different database operations that are going to happen when it seems like one simple thing you say, yeah, I want to buy this thing. All right. Okay, and that's, kind of stuff that we're talking about there. Now, as far as the process, one of the big things that Amazon relies on is locking. So items that are placed in a cart, in general, they're treated like you put something in your cart at a grocery store. And although it would be possible at a grocery store to reach into somebody's cart and take something, in general, people don't do that, right? That would be considered very rude, bordering on insane. The only time, I don't know, I remember a few years ago, there was a half-off sale on Nutella in France, and there were like riots in the grocery stores, right? And the reason why I mention is, you think about riots in stores, you think about Walmart at Christmas, but, I guess the French love their Nutella. What can you say? Okay. So anyway, something is placed in the cart. It's get locked so nobody else can access it, right? Amazon says, nope, this is for you until you decide what you're going to do with it, whether you're going to buy it or whether you're going to abort the buying process, and we'll return that product back to regular inventory, right? So there's two ways that could happen. Number one, if it's successful, right? You try to check out, your credit card gets validated, the fraud detection filter doesn't pick up anything suspicious. Amazon says, yeah, great, this is it. So in a sense, they can unlock the record, but in another sense, that product is effectively yours, right? But you'll be able to, look at it, see the status of it. The other thing, if the checkout fails for some reason, turns out you don't have a credit card at all, or you don't have a one with sufficient balance on it, sufficient credit remaining on it, or for some other, you abandon the process, there's some hardware failure, whatever, eventually all those items in your case will eventually be unlocked, right? Suppose you're shopping on Amazon and for no particular reason, you go into a coma that lasts for 2 years. Well, Amazon doesn't want those things to sit in the cart for 2 years, right? They will eventually unlock them. Now, how long it takes for stuff to unlock, that's kind of situational, right? I've seen things last for like a week in your cart before they get returned. I would imagine that if it's a popular item of limited stock around Christmas, they probably return it sooner. So that thing is flexible. They don't give you a specific time limit. Anyway, if the order goes through, the warehouse people are going to receive that order request, get such and such a book out the door. They'll make delivery arrangements with the supply chain people, probably an Amazon truck. They'll figure out which truck it's going to go on, and they'll give you an estimated delivery time based on that route. And then the inventory levels will get updated. Say, we have one less of these things in stock. Maybe we need to order some more. All right. Now, like I said earlier, in a single transaction, in general, there's a sequence of data updates that has to be followed, right? You have to enforce that sequence. So every process step, in a sense, happens as a unit. And every process step either succeeds, thereby enabling the next step, or fails, which tends to abort the process, right? Now, it's possible if you get to that checkout, you enter in a wrong credit card number, they'll give you some extra chances to do it, right? They'll say, oh, sorry, this is not a valid number, please try again. But at some point, if you simply don't have a credit card, yeah, it's going to fail at some point. And if they didn't do that, if they didn't enforce that kind of sequence, there would be a number of problems that could happen, right? The big thing would be things would happen out of order, and Amazon would have to dig into the system and undo some things that already happened, which is a big pain to do when the system is really designed to work fast one way and work sequentially that way. All right. Now, this is where we're touching back on some stuff from isolation, right? Remember ACID properties, remember isolation. So in principle, it's bad to allow multiple users access to the same data simultaneously. I'll give you an example. Okay. Oh, excuse me. Suppose a bank has two ATMs. We'll call it ATM 1, and because we're very creative, ATM 2. Okay, so we got two ATMs. Now, I'm standing at this one. This is me. I'm Doug, and I want to withdraw $500. Okay, this is my wife, who also wants to withdraw, typing's hard, $500. Okay, that's our plan. Good so far? Okay. Now, we can all understand the way this is supposed to go, right? It should go something like this. Step 1, log in. Step 2, request $500. Step 3, UI, well, let's see, how did I phrase that this morning? Let's see. Step 4, give the money. And step 4, update the database. Okay, and that's the way it should happen on this other side as well. So if both transactions are isolated, what that means in practice, rectangle really does, I don't know, maybe the mouse is shit, I don't know. Maybe it's, mouse is actually great. I think it's the surface. It doesn't always register clicks. What these things should do, they should both happen as self-contained units, right? So this process should happen and be complete, and I get my $500 and the database gets updated before this process starts. Or this process will start and finish before the process at my machine even starts. And that way, you know that the database is going to be correct. It's going to show that 2 withdrawals of $500 happened, right? But here's the problem that happens when you break isolation. I will show you. Okay. So there's a user interface between you and the database. So we've done a little bit of stuff in Access in labs, right? And perhaps we have done enough by now for you to know that if you make a change to a database, you just enter in a new number, right? You don't do math internal to the database. You have some other operation that calculates that math and then updates the contents of the database by overwriting whatever's, in a particular field. So what would happen, the user interface gets the balance, right? Finds account balance, reads account balance. Then the user interface application calculates new balance, right, based on that 500 withdrawal, and then C, the user interface writes the new balance, right? So the database is up to date. We'll bring that over. Actually, just copy it over. That's fine. Okay. And again, all this stuff, that should be in the bubble, and that should, all that green there should be the isolated part of the transaction. But if the transaction isn't isolated, then you can run into some very serious problems. So I'm going to mark off these with numbers, right? So it could happen that both my wife and I log into the machine at the exact same nanosecond as far as this process is concerned. We are in the machine at such a close time that all of our things are being processed basically simultaneously, all of our actions. So what could happen, this happens first, and then this happens. And then this happens, And then this happens. And at that point, the problem is already kind of irreversible. What happens at step D is both my view of the account, the application's view of the account on my machine, on ATM1 and ATM2, it's both showing that there's a $500 withdrawal from the account pending. But what'll happen if those C and D happen at like pretty much the same time, if they're not isolated, then E will write that new balance as original balance minus $500, and F here will likewise write the new balance as original balance minus $500. The bank will be out $500. So they'll figure out at some point that something went wrong, but by then my wife and I will have, left the country with our extra money, and then what are they going to do? Okay, now, you might fairly ask, why would that even happen, right? Shouldn't banks be aware of this kind of problem and prevent that sort of thing from happening? Yes, of course. In a well-designed system, this sort of problem is prevented, right? Because what happens is whoever logs into the system first is going to send a request to some governing process that's going to lock that database. It's going to say, okay, you are trying to do this withdrawal operation. Now nobody else can withdraw or even deposit money in that account until your withdrawal operation is complete. Whether it succeeds or fails, right? As long as that operation is still in progress, nobody else can look into that process and see it in some intermediate state. Okay, that's isolation. Again, in a well-designed system, this sort of stuff shouldn't happen. But what do we know about systems? If you were thinking not all systems are well designed, yes, that is correct. So here's a classic example. You guys have heard of Bitcoin, right? That's a joke. I know you've all heard of Bitcoin. Poloniex. You might not have heard of this, though. This was from close to 10 years ago now. Poloniex loses 12.3% of its Bitcoins in latest exchange hack. Okay, it was about $20 million worth. So if we scroll down a little bit, you can read the key text here. The hacker discovered that if you place several withdrawals all in practically the same instant, they get processed at more or less the same time. This will result in a negative balance, but valid insertions into the database. So what happens is exactly that problem there that I was talking about with the ATMs. What they had a governing process, but their governing process was calibrated to work in like milliseconds. The hackers figured out a way to launch a bunch of transaction requests within microseconds, right? Their governor process was flawed. And so the hackers were able to throw in so many requests so fast before the records were actually locked. So that happened. And I guess the key takeaway from this is your Bitcoin people, they're probably good at network stuff. They're probably really good at math and computer science type stuff. Database stuff, maybe not so much, but databases are important too. Okay. So when you allow multiple users access to the same data at the same time, one thing you can see is these interleaving of read and write operations, right? It's the same thing that I was talking about with the ATM, same thing that happened with the Bitcoin hack. You can also have what are called dirty reads. For example, imagine if you have 3 replicas of your account balance, right? And there's a transaction in progress. 1 or 2 of them have been updated. 1 or 2 of them maybe haven't. And if you are able to have multiple users access that stuff while the transaction is still pending, you don't really know which copy they're going to see. So the result is unpredictable. Something bad might happen, okay? Now, at Amazon's transaction rate, right, several hundred per second, it's inevitable that database operations will overlap. For example, if you run a query on a database, say, hey, show me a bunch of products, and Amazon's basically got to skim through an entire list of products, they're looking at that whole stuff. So in a sense, while that query is pending, nobody can, if they're following strict ACID properties, which they don't, if nobody can look at that section of the database, right? Nobody can try to alter anything. So if you have people coming to Amazon all the time to run queries on it, it even becomes difficult for the backend guys to make any changes to anything, right? Because why? Because anytime they're making a change with the ACID properties, that would prevent somebody on the outside from looking at that data. Anyway, so for these kind of problems, Amazon basically has three ways to deal with it. Number one, they can throttle the transaction rate. They can say, you know what, this system is too busy, we're having too much trouble keeping up with everything. We're just going to say, you know, people can only do so many transactions, and we're going to slow that all down, which would be a terrible approach to the problem in most cases. Why? Because people go to Amazon because it's fast and convenient. Same reason that, you know, Facebook doesn't want to throttle people's photo upload rate within reason. I mean, if you try to upload 10 terabytes of photos to Facebook, I'm sure at some point they'll pull the plug on you, right? But for normal, ordinary users, they're not going to say, sorry, you've uploaded 3 photos per hour. That's all we're going to let you do. All right. Nobody wants to throttle the transaction rate. That's like absolute last resort. Number two, sometimes what they do is group data in smaller or more isolated sets. For example, if you have a very large database table, you might create that as a bunch of segments, right? You might segment the table and store segments separately. So any operation, like if you're running a query on that entire database, you only have to scan through a much, much smaller segment. So that's a way of increasing the effective rate. Remember back at the end of the Facebook photo management lecture, talked a very little bit about MapReduce. We have a very big problem. We want to break it up into a set of smaller problems and run those smaller problems on separate machines to get the results faster. The same kind of thing there, right? So it's a way of doing that. But again, you can only do that so far. At a certain point, you know, you have diminishing marginal returns. Finally, in some cases, you might permit some simultaneous data access. Now, we've said here, in principle, it's bad to allow simultaneous access, right? It's bad to break isolation. But we also know that operations like Facebook, they have eventual consistency, right? Remember eventual consistency? So they don't always insist on all the ACID properties, including isolation. So what would make what would allow a situation where permitting simultaneous access would not be a big problem? Well, let me give an example where it is a big problem, right? For example, like with the Bitcoin hack, that's one. But imagine if Amazon has gift cards, which they do, right? You have gift cards. And imagine that people are using those gift cards on Amazon to buy things through other organizations that have posted stuff on Amazon, right? The various people, they're just posting their products through Amazon. And anytime you purchase something, Amazon sends a notification to them saying, yep, go ahead, you know, buy this stuff from them. But what happens if the bad guys kind of do the same thing that the Bitcoin exchange hack did, right? They say, we have one gift card number. We're going to run that like 1,000,000 times a second through Amazon's process, and Amazon's not going to catch it because their governing process is going to allow some temporary simultaneous access, send out all those requests with valid gift card numbers to all those different merchants selling through Amazon. That would be a very big problem, wouldn't it? Amazon would have to like desperately scramble to say, hey, don't send this stuff out, you know, but probably too late. It'd be like the end of one of those horror movies where one dude's running around trying to warn people, but it's all too late. Anyway, well, so that would be a case where it'd be very bad. But what would be the general reasons why you would permit simultaneous access? Who feels like talking? Nobody? Yeah.
Would it be like if two people in the same family are using the same account to buy things at the same time?
Probably not. I mean, I'm not saying like 100%, but see, the problem is you still end up in that same ATM problem, right? Where potentially transactions could go through in a way that they're not supposed to go through, where data is not correctly updated. So when we say simultaneous access, it's not about the users. It's not about even necessarily anybody trying to do anything bad. It's about this is definitely a problem. Anytime you allow simultaneous access, in particular simultaneous write operations, you have the possibility of that kind of interleaving, right? If you allow simultaneous access to users to write something at the same time, that could absolutely happen like the ATM. Likewise, dirty reads could absolutely happen, right? So if you break isolation, those are foreseeable problems. But under what circumstances would those not be big problems? I guess is what I'm asking. Yeah.
If you wanted to view the same thing, like if you wanted to show the multiple people the same list of items,
Yeah, why wouldn't that be a big problem?
because then they could see everything, but they're not doing anything with that information.
Yeah, they're not doing anything, right? So good. One example, imagine if you have a very popular holiday item, like there was a thing called the Furby around 1997. For all I know, some of you had Furbies as kids. Anyway, whenever it came out, it was a very popular thing. And Amazon, a lot of people go to Amazon, they look and see if they can buy a Furby, right? Maybe at any given moment you have 10,000 different viewers going to Amazon to look at the Furby page. Now, problem with that, if you insist on isolation, remember all those web pages and all the data associated appear on those web pages. What the fuck? Has to be pulled from a database. I've been getting a lot of really annoying phone calls lately. Can't talk to you guys. Hello. I'm good. I'm in the middle of my lecture, so I have a 4 o'clock appointment today, I think. Oh yeah, tomorrow, Thursday. Yeah, great. Thank you. Yep. Bye bye. We thought our dog was maybe dying last couple of weeks ago, but it turns out he just had a bad leg, so that was the bet. Anyway. Okay. So in general, if people can't do any damage with this kind of data, if the data itself is something that, yeah, you're going to show people, but either number one, it's like in a read-only format, or number two, no real serious damage could ever happen, then yeah, you can live with that. For example, the example I give with Facebook, you post a photo on Facebook, maybe Facebook echoes it to multiple data centers on opposite sides of the world, and it doesn't really matter if one of those copies for a little while shows that it has 8 likes and another one for a little while shows that it has 9 likes. Because why? Because number one, there's no real cost to that, right? Facebook will like sort it out. First of all, probably nobody will even ever notice. Number two, even if anybody does notice, what are they going to do? Call up Facebook and say, hey man, I'm super pissed. You posted my photo and at 10:33 p.m. it briefly had 5 likes in California, but only 4 likes in Japan. And Facebook will be like, what, why are you bothering me with this, right? So in some cases, either the data doesn't matter, or if it's strictly read-only kind of format, then yeah, no real damage is going to happen. Okay? Okay. Now, if multiple users do simultaneously try to buy the same last thing, right, that could happen. Now, what happens on Facebook is they have a thing, there's a thing called Ajax on web pages, and I don't need to go into detail about it, but you know how when you go to Amazon and you look at a product and it'll be a little green thing that says there's only 4 left, hurry, buy now if you want one, and that can be dynamically updated. Like if you actually do buy one, then you can go back and see that the count has dropped by 1. That mechanism for updating little pieces of a web page is called Ajax, and Amazon is going to update that, as they need to. Okay, but suppose you get to a page and it says there is just one, right? It's some outside seller who has this one unique item that they're only have one of to sell, and so whoever buys it gets it, right? So what could happen? Of course, 2 people get to the same item at the exact same time. They both click their mouse at the exact same time. But you know what? Only one of them is going to win. I don't know how the tiebreak is going to be resolved, but obviously things arrive at the database sequentially in some sense. One of those people is going to get the item, and the other one is going to be disappointed. But that's life, right? So that for Amazon, we understand that that's a foreseeable hazard of retail shopping. But there are other problems where that's much more serious, right? So imagine if you're buying concert tickets, right? So how does that work on Ticketmaster? You go to Ticketmaster, you tell them the show you want to see. They'll display like a map of the venue with all the different seating sections, right? And you pick what you want. And if you pick what you want, what section, Ticketmaster will offer up, oh, here's a couple tickets randomly selected from this area. And either you don't like them and you throw them back, or you do like them and you go on to the next step of the process, right, where you start to pay for them. Now, of course, you have only a few minutes to decide, right? Ticketmaster is going to say, do you approve these tickets? You must decide in the next, 2 minutes, or we're going to throw them back into the pool. So same kind of thing there. Now, I know airlines also tend to overbook. This does happen. But in general, if you reserve a seat on an airplane, you're going to get that seat, right? The airlines do not like to have multiple people book the same seat because it obviously creates a lot of tension on the plane. Sometimes, newsworthy incidents. So for Amazon, for retail, it's not that big of a deal if multiple users simultaneously buy the last thing. Because why? Because in a very real sense, they can't. Now, if there's a stream of items, right? So for example, this berry blue drink here, this might be discontinued now. I was able to find some on Amazon, might be discontinued, might not be, but say it is. Say it isn't, rather. If I buy like the last one that they have right now, there's a pretty good chance that there'll be, some more in the pipeline will arrive tomorrow. And the user will only experience that as, Amazon will apologize, say, oh, we had some temporary delay. Your stuff isn't arriving today. It's going to arrive tomorrow afternoon, right? So in most cases for Amazon, this sort of same last item issue, not a big deal. For other things like seating reservations, it can be a big deal. This one, though, trying to use the same gift card, that could potentially play out kind of like the Bitcoin hack. Imagine, worst case, people buy some kind of Amazon gift card and they're somehow able to convert it to cash at some outside operation, right? There's some operation that, basically treats it same as cash and you immediately get the stuff, or you can withdraw money based on that. Well, if the bad guys figure out a way to run a whole bunch of that through the system at the same time with the Bitcoin, like the Bitcoin hack, yeah, that would be a huge problem. So again, the solution for this is generally what's called locking. And locking means if one user is using a particular thing, a particular record or set of records or set of fields or an entire table in a database, it's locked so no other people can use it, right? They can't even peek into it. This is what provides isolation. Now, practical real-world problems. Number one, how long should a lock last? Though I've said some products on Amazon, I've seen them stay in my cart for a week. I imagine very popular products, with an urgency to sell, probably be much shorter. If it's something like concert tickets, imagine if some asshole went on to Ticketmaster and just bought a whole bunch of tickets, but that didn't actually buy them, right? Just claimed them through the normal process and then just sat on them, right? Didn't say yes, didn't say no, and there wasn't a timer there, right? That'd be a real dick move, but I'm not saying nobody would do it. Okay, so obviously there's going to be some sort of mechanism for determining when a lock is going to naturally time out, and that's going to be, system dependent. Number two, how many things can a single user lock? Imagine if Amazon didn't have a limit on its shopping cart, and malicious guys could go to Amazon and try to buy literally everything, right? They would fill their shopping cart with millions and millions and millions of dollars worth of items. And if one guy can do it, a million guys could do it at the same time, right? They could all just swarm Amazon, load everything into their carts so that nobody could buy anything, right? Which would be some very interesting corporate sabotage. So again, yes, Amazon puts a limit on how many things a single user can lock. Or for example, you go to Ticketmaster, right? I'm not sure what the seat limit is. It might be specific for different venues. But last I checked, I feel like it was 4 was the most tickets you could try to grab at once. So yeah, that would be like, you can only lock 4 things at a time. And we have 2 related problems, Deadlock and Livelock, which we'll talk about now. Okay, so first of all, Deadlock, which we briefly mentioned before. In Deadlock, 2 database actions actually block each other. So we're gonna write this out. Imagine if, let me follow the text of the slides. Okay, you have a user U tries to update records A and B, while another user named V tries to update records B and A. Right? For some reason, that's the way that the modify operations were sequenced. So what would happen? U locks A and V locks B, right? So then when U checks B, it finds it locked. And when V checks A, it finds it locked, right? Both operations are halted with no way forward until they time out. And this is bad. It's bad, first of all, for that one user, but imagine if the database system is following strict ACID properties and saying that, oh, there's some stuff going on with this database. If some other user is trying to do a query on the database, right, on that section of it, that query can't go through, right, because these records are in transition. It's going to lock up stuff for a lot of people. If the database is already busy and people are having, some trouble getting what they need fast, the fact that these kind of operations happen and are locking it up for everybody is just going to make that whole setup worse, right? So this is what, you see the wheel spin around for a while, and finally it'll say, sorry, we could not complete your request. Please try again in a few moments. Okay, so deadlock is bad. Remember, it's called deadlock because the system is locked and it's dead. It's not doing anything, right? Both processes are waiting for the other one to, in some sense, be available to make the lock go away. Now, the alternate thing to that is livelock. So livelock means the system is responding in some sense to the block, but responding in a way that perpetuates the block. So a non-technical example. Imagine if you're walking down a narrow hallway just wide enough for two people, and you're walking on your right side, and another person is walking towards you on their left, right? You're both on the same side of the hallway. Eventually, you'll get close enough where you both decide to stop playing chicken with each other, and what happens? You both take a step to the side. But when you go to your left, the other person goes to their right, and guess what? You're still blocking each other, right? So then you do the same thing after a minute. You realize, oh, this is weird, and you take the step back. But the other person does the same thing at the same time, right? We've all experienced this at least once in our lives, and then you and the other person look at each other and you laugh about how stupid the universe is, then you figure out a way to get past each other. That's livelock, okay? Now, with livelock could happen by something like one possible causes here for this situation. Number one, retrying query or retrying update with the sequence reversed. Right? So for example, U updates B then A while B updates A then B, right? You're going to have the exact same problem, just reversed, right? But still both operations are going to find the second record is going to be locked. Or retrying the update after a fixed delay, right? If you say, okay, we're going to try this again in exactly 5 seconds or exactly 3 minutes and see what happens, and they try it again, well, guess what? Both of these actions are going to happen at the exact same time again, and you're going to be in the same problem. Now, of course, put this in orange. In a well-designed system, deadlock and livelock should not happen, right? But of course, not all systems are well designed. This can happen. And even, even in a well-designed system, there is always a possibility that, users will have to wait on other processes, right? Hopefully they happen fast enough so it's not a big problem. But if the database gets busy enough and can't keep up with all the activity, then yeah, this is the sort of thing that, it can feel like deadlock, right? Just you're waiting in the queue for everything else to get processed. Okay, but that's not true. That's not true deadlock. Okay. And this seems like a good break point because this is where I left off this morning. Would anyone like to know more? All right, one thing, I'm going to go back to my office right now and post up the exam grades. I have them. I posted up the morning ones, but now I got to post them for you guys. So I'm going to go do that. All right. Have a good day.